A new method uses optics to accelerate machine learning computations on smart speakers and other low power connected devices. Ask a smart home device for the weather forecast and it takes several seconds for the device to respond. One reason this latency occurs is because connected devices don't have enough memory or power to store and run the enormous machine learning models needed for the device to understand what a user is asking of it. The model is stored in a data center that may be hundreds of miles away, where the answer is computed and sent to the device. MIT researchers have created a new method for computing directly on these devices, which drastically reduces this latency. Their technique shifts the memory-intensive steps of running a machine learning model to a central server where components of the model are encoded onto light waves. The waves are transmitted to a connected device using fiber optics, which enables tons of data to be sent lightning fast through a network. The receiver then employs a simple optical device that rapidly performs computations using the parts of a model carried by those light waves. This technique leads to more than 100-fold improvement in energy efficiency when compared to other methods. It could also improve security since a user's data do not need to be transferred to a central location for computation. This research is published in the journal Science. This method could enable a self-driving car to make decisions in real time while using just a tiny percentage of the energy currently required by power-hungry computers. It could also allow a user to have a latency-free conversation with their smart home device, be used for live video processing over cellular networks, or even enable high-speed image classification on a spacecraft millions of miles from Earth. Neural networks are machine learning models that use layers of connected nodes or neurons to recognize patterns in datasets and perform tasks like classifying images or recognizing speech. But these models can contain billions of weight parameters, which are numeric values that transform input data as they are processed. These weights must be stored in memory. At the same time, the data transformation process involves billions of algebraic computations which require a great deal of power to perform. The process of fetching data from memory and moving them to the parts of a computer that do the actual computation is one of the biggest limiting factors to speed and energy efficiency. Netcast is the name of the neural network architecture developed by the MIT researchers. Netcast involves storing weights in a central server that is connected to a novel piece of hardware called a smart transceiver. This smart transceiver, a thumb-sized chip that can receive and transmit data, uses technology known as silicon photonics to fetch trillions of weights from memory each second. It receives weights as electrical signals and imprints them onto light waves. Since the weight data are encoded as bits, ones and zeros, the transceiver converts them by switching lasers. A laser is turned on for a 1 and off for a 0. It combines these light waves and then periodically transfers them through a fiber optic network so a client device doesn't need to query the server to receive them. Once the light waves arrive at the client device, a simple optical component known as a broadband Mach-Zehnder modulator uses them to perform super-fast analog computation. This involves encoding input data from the device such as sensor information onto the weights. Then it sends each individual wavelength to a receiver that detects the light and measures the result of the computation. The researchers devised a way to use this modulator to do trillions of multiplications per second, which vastly increases the speed of computation on the device while using only a tiny amount of power. They tested this architecture by sending weights over an 86-kilometer fiber that connects their lab to MIT Lingen laboratory. Netcast enabled the machine learning with high accuracy, 98.7% for image classification and 98.8% for digit recognition at rapid speeds. Moving forward, the researchers want to iterate on the smart transceiver chip to achieve even better performance. They also want to miniaturize the receiver, which is currently the size of a shoebox, down to the size of a single chip, so it could fit onto a smart device like a cell phone.